Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah. And then I would fall asleep anyway.
It is a pleasure to welcome Arthur Gustavus from Boston University here at Microsoft. Arthur got his PhD in 1992 from Harvard University. He is the chairman of the computer science department at Boston University. He's been doing research in many areas of networking and real-time systems, including generalization of the classical rate monotonic analysis to accommodate probabilistic guarantees. The first model for internet content distribution, and today Arthur will be talking about strategy flexibility.
Oh, thank you, Marcus. Thank you all for coming. It's good to be here. This is my third day at Microsoft, and I have to say I really enjoyed every minute of it. So let me start by saying this is work in collaboration with a number of graduate students. Yuting Zhang, who is spending her internship at VMware, which of course you know is related to this. Mina Girgis, who's a student of mine, spending an internship in a security company. Ibrahim Mata, a faculty, a colleague, and Rich West is also another faculty member. So let me start with why we are doing this research and why this is exciting. And maybe I don't need to sell this to you, but I do believe maybe I should just tell you a little bit about it. So first of all, it is clear that virtual machine abstractions are gaining acceptance. Everybody's talking about them. There's companies that are viable. Microsoft has a version of this, VMware, etc. And so far, people have been talking about virtual machines as used primarily in closed managed environments. So basically, you want to consolidate servers. You don't want to have too many servers. And you want to do development or testing. And you may want to have multiple people not affect each other. So this is one sort of vertical. By the way, these are directly from VMware's marketing material, enterprise IT, training, etc. So this is key. So far, people have been thinking about it as being used in a closed environment, where you own the host. Everybody who's going to share that host is part of the team, friendly. Okay, trend number 2. Well, we are starting to see lots of applications running on third-party hosts. This is straight out of Spedera, where recently acquired by Akamai, where they say, well, you develop applications and so on. Instead of just replicating content to replicate the whole application, just give me a binary image, and we'll just push it out, and we'll do the trick. We'll do it for you. So clearly, the person developing the application doesn't own the infrastructure on which the application is going to run. And clearly, to be profitable, this infrastructure has to support many applications and many other parties, not just this one. Another example is IBM. Another one, which is in the research side of things, I don't know how many of you have heard of Planet Lab, very big in the networking community. The idea there is, well, we would like to have networking researchers play with the internet. Well, but they need to put probes, all over cyberspace, all over the network. How do we do that? Well, let's get a bunch of hosts, connect them with the network, and allow them to run their tests all over the world. So every contributing entity, like BU, we contribute 5 machines. They're sitting in our lab, but they're really Planet Lab machines. So you get this overlay of hosts all over the globe, actually, lots of them, thousands of them. And the idea is, again, there will be somebody running on this machine that I don't know. They just put their experiments there. They want to run it. And they're not going to be the only one using the machine. Lots of other experiments are running. Okay, so if you think about it, these are applications sharing a host that really is part of an infrastructure. They don't own it. The third trend, and I'm going to talk about this a little bit more, is that, of course, we need to isolate these entities running on these hosts from each other. this actually started appearing as a problem from very early on, 2001 and even earlier, where web hosting was still an interesting commercial application. People will buy a host and put lots of web servers on it. And then the question was, so I put my nonprofit organization website on it, and next to me there's somebody doing X-rated stuff. Hosted on the same machine, well, they suck all the resources, and the performance of my website is very bad. So clearly there was need to do some isolation, which give a lot of use for traffic engineering and all that. Planet Lab is concerned about this. This is straight out of Planet Lab architecture today. So in a Planet Lab architecture, they envision one host. This is one of the thousands of hosts they will have, where in this host there is multiple entities that have to run their own environments. For example, the owner of the machine may want to have their own virtual machine if you want, or their own space. But also you may want the people running the experiments on it. These are the users. And you may have lots of VMs for users, the user from University of Washington, the user from MIT, the user from BU, etc. In addition, you need these management sort of users. So, and the way they will do it is by having multiple virtual machines share on top of a VMM. That's exactly how they do it. They just want to have all their machines do that. So let me tell you about one particular case that we have at BU that we also want to do. So this is along the third line where we have these shared overlays and grids, etc. So I'm going to take just 5 minutes to tell you about another project, but you'll see why solving this isolation problem is very important. So imagine our networked world of sensor actuators, processor storage, and I imagine this to be like in a mall, in an airport, where somebody builds the mall and they just put all that stuff in the walls. It's part of the infrastructure. Now, they don't actually own or care about the applications that will run on it, but it's value added. If you put your store in my mall, you don't have to put your own cameras. It's there already. Okay. So actually, it's not hard to imagine. Say, imagine, this is happening. I don't really need to imagine. It's happening at BU. We got a large grant from NSF a couple of years ago to actually try some of these ideas. So we are building what's called the Sensorium. The Sensorium is a whole bunch of cameras. So we're going to put, overlay on top of the lab and in offices. And we think of a Sensorium as a common space that's equipped with video sensors. And for the particular application of ubiquitous recognition, tracking of activities, etc., human-computer interactions. So this infrastructure consists of sensing elements. Well, we are in particular, video sensing elements in our case, but in general, sensing elements. Programmable network, you can play with it. It's all under your control. Compute engines, where you can actually do quite a bit of CPU-intensive computation on this infrastructure. Storage, etc. Okay, so why would anybody want this? Well, here's the mandatory list of possible applications: assisted environment, safety monitoring, etc., etc. I think you have seen these in lots of other talks. So one of the projects we're working on, which is very interesting, and this is in collaboration with Asaf Kufuri, who's also faculty in our department from the software systems side, is a project called Sensor Network Bench, Programming Workbench, snBench. So think about somebody who's trying now to use that infrastructure. It's in the mall, and they want to write a little application. So they're sitting here. What do you think they should do? Should they think about individual sensors, individual wires, individual nodes to do computation? Clearly, that's not scalable. It's just not manageable. You don't want them to do that. Moreover, they may want to write this application to run in many malls, not just one. So here's the fire department. They come in, they want to write, or the police department. They want to execute a query on this mall. They don't want to rewrite their code for every possible mall they'll go to, or airport, etc. It would be nice if they have the same program, and you say, well, here's your infrastructure. Try to execute it. Try to run it. Try to compile it on that infrastructure. That's precisely what snBench is about. Our goal is write once and run wherever. So you want to write the application for the distributed sensor network application once, but run it anywhere. It doesn't matter whether you have this kind of camera, that kind of camera, this much bandwidth, not that much bandwidth. We don't want the programmers to program nodes. We want them to program the network, a virtual computer, basically. So, okay, so I'm going to skip this. I mean, I can give you a separate talk on this project. But the point here is we're going to start with these building blocks of sensors, some stock algorithms like edge detection, face recognition. They're not specific to particular infrastructure. We're going to glue them together with some high-level language that includes the usual suspect conditional loops and things of this sort. And we'll just pretend there is no network. And just here is your code. And of course, that code has to get transformed and sort of dissected into pieces that will go and run on the different sensors and elements and so on. As a matter of fact, here's the programming cycle for snBench. You program. So you're going to write a program in a language you call snafu. It's functional. This is what the FU comes from. And of course, if you know my colleagues at Boston University, you had to assume it has to be functional, but actually for very good reasons. We are going to compile that snafu program into an intermediate representation we call step. I'm not getting into the details because that's actually a subject of a different talk. I just want to get to one point here. Once we have this intermediate representation, we have to map it to the infrastructure. So we have to take that step plan, as we call it, and then we have to decompose it into smaller pieces that we know how to glue together and send these off to the various parts of our infrastructure. Now, I want you to think about this as a second phase of the compilation. This is a compilation, but this is also a compilation. As a matter of fact, at the end of this step, the system can come back and say, sorry, I cannot compile on this infrastructure. You don't have enough cameras, you don't have this, that, including you don't have enough bandwidth. Currently there's too many other applications running. I cannot do this for you, etc. So this is really an involved step. There's a lot of research to go here. Again, another subject. But finally, this actually is also very interesting. At some point, I have to dispatch this. So this step plans, now that I've figured them out, gets dispatched and literally loaded into Sensorium execution environments, what we call SXEs. These SXEs are where these things are going to run. These are, quote unquote, the virtual machines. So the picture we have is that we have all these elements in our network. And on every one of them, we'll have an execution environment. Very, very small, maybe modes, etc., but also very large, powerful CPUs, etc. Now, we need to isolate these SXEs because you will have one SXE per piece, and these pieces may belong to different applications. We need to protect them from each other. We need to isolate them from each other. So this was very high up. Now I'm going to talk about just one of these SXEs, in particular, let's say a Linux box. And I'm going to think about how do I protect different virtual machines running inside these boxes, each one of them working on behalf of a different piece of a different application. So what kind of isolations do people talk about when they talk about virtual machine isolation? They talk about memory isolation. This is quote unquote from, since I was coming to Microsoft, I said, okay, I'll look at what they say in the virtual server. So VMs provide robust, secure isolation between host and guest memory address spaces. That's actually originally one of the main reasons for these VMs, is isolating the memory, for example. Or failure isolation. We don't want that somebody crashing the operating system to crash everybody else using it. So they can crash inside their own space, but that's not going to affect other VMs. And this is what I want to talk about today. So these, granted, this is exactly what VMs are supposed to be doing, but I'm worried about this one. I need to ensure that a VM does not monopolize the host resources it's on to the detriment of other VMs sharing that host or sharing the infrastructure. I'm going to focus about hosts that are, computers, but in general, this could be a grid, it could be a very, very small device, etc. So let's go down one level. This is sort of the motivation introduction, the big picture. Well, if I have a host and it's under provisions, because I have, one too many VMs running on it, what could happen? Well, if there is not enough resources, you get overload. Two things may happen, actually, amongst many. For example, if these different VMs running different applications start asking for more resources, well, they're asking too much, systems start crashing, your underlying system may break. Well, clearly, we have violated this crash protection, if you want. But more realistically, because maybe you can design this so that this doesn't happen. But how about this scenario where a couple of applications squeeze the other applications out of existence. How? Well, imagine if these guys, for example, are doing something real time. They're not getting enough resources. Well, they're useless. Think about the Sensorium applications I was talking about. If you cannot send the frames at the right rate, right? So this is something we have to protect them against. Well, how do we do that? Three different approaches. The first one is, well, this is just another case where the operating system has to be careful about giving resources. So the hosting operating system or the VMM running underneath will have to include the smarts to do micromanagement. So it will have to figure out, okay, you're real-time, you're not real-time, I'll give you higher priority, lower priority. Typical scheduling like we've learned in any operating systems course. And we'll have to do this. Maybe you have to design special APIs, or you can tell me the QoS, et cetera, et cetera. So, well, maybe you agree, maybe you don't, but I believe that this adds complexity to that common infrastructure. This host, in my opinion, has to be as simple as possible, because then it's going to be efficient, fast, et cetera. This is what we learned from many, many years of building systems. Also, it is unlikely to know the application's ability to adapt. The host doesn't know what's running inside these VMs. And to make it aware of it is huge. You have to communicate, and that's not a good idea. It may well be the case that as an application, I can slow down my requests from resources in order to adapt. It is also not easily extensible to multiple resources. Maybe I can schedule CPU. Maybe I can schedule disk. But what if you have lots of resources on your host? And the congestion is on different resources. You have multi-resource scheduling problems, which are very difficult. Okay, so this is approach number one. This is not our approach. I just feel like I have to talk about it. The second one is reservation-based. Well, before you start anything, tell me what's your maximum requirement. I'll just make sure I have enough. People are not going to step on each other's toes because I reserved things. This is very inefficient, especially for very highly dynamic applications that may, worst case, want 100 times what they need on average. Well, that will be very hard to. So this is what real-time people have been doing, for scheduling and things of this sort. Well, of course, we can do the good old best effort, which is do nothing, or just simple common infrastructure. You just have to live with the resources. That's the picture I had before, when one application may be squeezed out of existence. Okay, well, that could be possible. It's not fair. It's not predictable. So this is good here, simple infrastructure, but nothing else is good. So what I want is the following. This is my wish list now. My wish list is I want a simple hosting infrastructure, just like the best effort case. Maybe I will want it to do some macro management. For example, do policing. Policing is very different than resource allocation. Resource allocation, I decide who gets what next. Policing says you have had enough over the last 2 minutes. Okay, you are not playing by the rules. Out. Okay, that's very different than deciding who gets the next slice of the resource. So this is sort of more of a macro management. The second bullet on my wish list is application autonomy. There shouldn't be coordination between applications. These are run by different entities. They don't know each other. They shouldn't know each other. They should be totally autonomous. Not between the application and another one, and not between the application and the operating system or the underlying host. Why? Because maybe today I'm running it on the VMM that Marcus is working on, and tomorrow I'll be working on the one that VMware is working on, and there are different APIs and different ways of seeing the world. So I shouldn't assume, basically, that there's functionality provided from below. Clearly, we want the performance isolation. I want to make sure that when I put these applications together on the same host, they converge to a fair allocation of the resources on which they're competing. Okay? So I don't want one to get everything and the other is not getting much. And I want to make sure that my resources are used efficiently, which means no thrashing. So I'm operating in nice space in terms of the infrastructure. So how I'm going to do all of this? Our solution is the end-to-end style. So I actually do research in networking, and I saw this as an opportunity to sort of apply something we learned in networking to building systems. And I want to see, well, how far can I push this analogy? Well, basically, you can think about the host as the shared infrastructure as the network. Minimal functionality, best effort, round-robin style resource allocation. So So round robin, I'll give you the resource you want. Now, in addition, I may want the network, and I'll talk about this later, but this is not required. This will be nice if the host will give me some signal as to how congested it is. Are you really overloaded or not? But, I don't need this. I'll figure it out myself if need be. So it would be nice to have that. And also, it would be nice if the host can do this policing functionality, where it says, if you don't behave, I'll kick you out. But again, I don't need it. But, well, I would need it if I really want people to not be heard. But, at least for our experiments, we don't need it. On the other hand, what I want from applications is the following. The application should be able to probe, to figure out what's available, how much I should ask for. Should I fork yet another process to do a web, let's say I'll do a multi-threaded web server. Do I need to get more threads? Or, well, it's a decision the application has to do. Should I acquire more memory or not, etc. Every application, I'll talk about this later, may have different ways to adapt to overload condition. It may be okay for you to cut down the memory you're using by half all of a sudden. But for another application, it may not be all right to do that. You may have to do it slowly, because maybe it's real time and you have to sort of do things in a smoother. So how you adapt may depend on the application. So I don't want to have one size fits all for the application. As long as you adapt according to some rules, it's fine. And finally, I need to define for every application what it means to be friendly. What it means that it's nice to share the host with you, my friend, okay, because you are a nice application. You are not going to hurt me. So if all of us are nice to each other, that's the world I want to live in, basically.
And not niceness leads to policing and being...
Exactly. That's why I need this. So this will be the incentive for people to do policing. There is another way to do this, which I'll talk about later, which is if you can certify that something is friendly ahead of time, then you don't load it unless it's certified. Now, how I would do that, that's actually what Asaf Kfouri, my colleague, does. The compilers can do that, and I'll talk about this later. So the compiler can say, this guy is certified to be nice, because I have added the code for it. So we'll talk about this. It's actually a very interesting subject. So this is sort of our top, and from now on, you've got the message. This is what I want to do, and you'll see how I implement it. Yes?
Could you back up a slide?
You bet.
It seems like one of your requests was...
okay, this one.
Yeah, that there's no explicit coordination with the host,
Yes.
but you're violating that by requiring them to do adaptation.
No?
Okay.
I'm not telling the host to do anything on my behalf. I'm just gonna, I'll give you the analogy of eating. Okay, so we are on an island. There is just limited supply of food. I can be greedy and just eat everything I can have. That will starve others. Okay. Now you can argue I can get sort of feedback and coordinate. What I can do is, what I need to be able to do is figure out that the food is not in great supply. What I will do now is I'm going to eat less. I don't know how much you're eating. I have no idea. And I'm not telling, whoever is providing the food not to give me food. They actually give it to me if I ask for it. That's exactly the best effort part up here. They will give you the resource if you ask for it, but you're not going to ask for it because you realize that if I ask for it, it's not fair to others, I would not converge, etc., etc. So there's no explicit communication, there's indirect communication. It's almost like, so let's take the network analogy, which is actually coming up. Okay, so look at this slide. So this is the picture people use everywhere about these virtual machines. They say, okay, you have resources, part of an infrastructure, managed by a hosting environment, some operating system, VMM, whatever, running applications, and so the application running in these little sort of bubbles on their own. And think about this as the user getting the results of the application. Well, I'm just going to do a little animation, and I have to admit I'm not very good with animation, but I spend a lot of time on this one, so you better like it. So I'm going to put the user on one end, the application on the other end, the hosting environment in the middle, the resources are part of the hosting environment, and the user is getting the service from the applications. And I actually drew this on purpose this way. Look at what I do. I'm showing these lines not going through all resources, but going through only one. Actually, in fact, they may be going through all of these resources, all n resources or a subset of them. But what I'm showing is the resource for which they are congested. This is their If they're CPU bound, it's CPU. If it's I/O bound, it's the I/O. If it's network bound, it's the network. So every application, this is the contention, every application is going to be hungry for one resource more than any other. It is the one that's throttling it.
At different times.
At different time, absolutely. But isn't that the same with the network? So if you think about the networking environment, these resources are being shared by flows. For a given flow at a given point in time, it has one router where it's losing its packets from. Or at least we assume that. Most of its packets are lost in one place. And now, which ones of these applications on the left should sort of be concerned about each other? Well, I claim that these guys have nothing, they shouldn't compete. They are in sort of different spheres. Let me go back to one of my desirable properties. It's here. I have to emphasize this. It's a very important point. Applications with different bottlenecks need not tussle. If you are hungry for CPU and I'm hungry for networking, we have no business fighting. Yes.
I could be consuming resource number 2, even though it's a bottleneck for 1.
Yes.
And he is consuming resource number 2 and bottleneck on it.
Yes.
So I'm still taking some part
Yes.
of 2,
Yes.
but I'm not necessarily bottleneck on it.
Correct. So the
Or I'm
key,
less bottleneck on it than 1.
that's the point. So let me put it in a queuing theory way of thinking. So if you think about a queuing network, where are you spending all your waiting time? If you're spending all your waiting time at resource number 1, even though you're using resource number 2, then I shouldn't penalize you on resource number 2. That's the point. In other words, you are paying your tax on that resource because that's where you're spending all your queuing time. Okay, and the point is, if everybody's going to be throttled by something. So this is exactly what happens on the network. You are going through multiple buffers. You may be using a buffer for which I'm congested, but I'm also using it. But it turns out that because you lose most of your packets on that second buffer, that's what TCP adjusts to. It doesn't adjust to the first one. It's noise for all practical purposes.
You're assuming the TCP behavior is the ideal backoff behavior.
Well, I'm going to talk about different backup behaviors, but we certainly tried the IMG version, so we'll talk about that. So, okay, so let's go back. Okay, here's the animation one more time. So I do define applications that are sharing a particular resource as bottleneck equivalent. These guys are bottleneck equivalents. For all practical purposes, they should tussle. You know, this guy, maybe others should tussle over this, etc. So this is the E2E analogy from networking. And now I've actually intentionally talked about applications. Well, a VM is just another application. The nice thing about VMs as an application is that you write one VM and it will be used by lots of people. So it's a natural application to make friendly. You know, I can also take a web server and make friendly. I can make my sorting algorithm friendly. But, you know, and I'll talk about these later, but so as people want to prove this point, we said, so what should be the great application we should try? And VMs was very natural. Okay? So think about now a VM as an application. It does need to provide this isolation, performance, etc. And today's hosts are powerful enough to run multiple of these. And VMs will compete for host resources that are very different. You may have a VM running something that needs a lot of memory, another one lots of network, another one lots of I/O, etc. So here is the solution now cast in terms of virtual machines. Virtual machines should adapt the resource consumption rate, based on congestion feedback signal that I've got from the system. The benefits is minimal, okay, I'm repeating what I said before, minimal management from the operating system, which is good. I'll show that this will result in convergence to a fair allocation of the resources and efficient use of the resources. And it's transparent to the applications running on top of the VM. Applications running on top of the VM don't know that the VM is doing this. And it's transparent to the host. The host doesn't know that anybody is adapting. It's not thrashing. So I will show you results where without what we have done, Linux starts doing ridiculous things to avoid thrashing, which hurts everybody. And then you just turn on this friendliness, and somehow it just never gets into it because people are sort of... Okay, so what are the elements of this solution? Well, we have to come up with 3 answers. Remember the 3 underlying things. I have to figure out what is a feedback signal, how to control the consumption rate of a VM, and how do I adapt now that I know that it's congestion. Okay, these are the elements of our friendly virtual machine framework. So let's answer the first one. So in virtual machine, there's this notion of a virtual clock time, VCT. What is a virtual clock time? Virtual clock time is the time interval, the real-time interval between when the clock on the virtual machine ticked and then it will tick again. Think about it as somebody is emulating a real clock. But since I'm doing this in a virtual environment, here's a clock tick, and then a while, maybe I got context switches, whatever. Now here's another clock tick. The real-time difference between these two ticks is called the virtual clock time. In many ways, you can think about the virtual clock time as the response time of the virtual machine. If you think of the virtual machine as something you get a transaction from, well, every time the clock ticks, it's like a new transaction and I succeeded. If the time it takes between ticks goes bigger, it means response time is bad, right? So to sort of show you this, consider the following VMs running on a host. So at time T1, this one was running. At some point later, context switching, this one is running. And let's say these guys are blocked for whatever. And now we go back and give this one a time slice. So because the counter went from 1 to 2, that is the VCT for this one. And now I want to show you what happens if more VMs start competing for CPU in this case. What will happen is, well, we repeat the whole thing. So here's VM, next time slice, next time slice, next time slice. What happened? What is VCT? Oh, it's much bigger now because it took me that much longer to come back to this guy. Now, you notice that, well, I can repeat this, right? So what if I have 6? Well, it's just going to be linear in the number of VMs sharing the infrastructure. Oh, that's great. If it's linear, it's great. It means the system is efficient, correct? The problem is when it becomes superlinear. So in particular, as the number of VMs increases demand of a resource, because they're all going for it, let's say CPU, well, the utilization of the resource will go up. And we know what happens when utilization goes up. Originally, it starts nice and linear, or close to linear, but then it hits that knee and shoots up. So as long as VCT is going up, but in a linear fashion, I know that I haven't hit that knee yet. It's when I hit this that I should be careful. That's the congestion. I want to avoid being here. Okay? As a matter of fact, because you hit that threshold, your service rate will go down, and that's basically the onset of thrashing. So as VCT grows linearly, that's an efficient use of the resource. When it starts to be super linear, that's when it's not efficient. And by the way, this is true of, I don't want to say all resources, but most resources. Because, think about network, again, you cannot go with window size less than 1. It just, things will go drastically bad, for example, not just CPUs. So this is where we're going to get our congestion signal, but still, I'm giving you an example of VCT. Now remember that VCT is something that the virtual machine can measure at any point, at will. Why? All it has to do is just read the current real clock time every time it gets scheduled. So every time a context switch, the first thing it does, okay, tell me what's the real time. Okay? I will tell you about other ways to do it as well. But So as I mentioned, this is thrashing. You want to avoid being in this region, so you want to really stop things here. How are we going to do this? Well, at any point in time, we are going to denote by VCT of t the virtual clock time at time t. That's an instantaneous thing, which is likely to be very bursty, because it depends. Scheduling is very fine-grained. Things are going to be very... So instead of relying on VCT, we're going to take an exponentially weighted moving average of it. So we're going to do basically the instantaneous value of VT multiplied by some gamma, and then the previous estimate 1 minus gamma. And then over a window of time, let's say W, 2 minutes, 1 minute, I'm going also to observe the minimum VCT I've seen. That's the best case scenario. If I'm the only one on this host, this is what I will get. Okay? Those of you who know networking will realize it's very similar to what's called TCP Vegas. Vegas does that. It figures out the round trip time computes an average over multiple packets, and it keeps track of the minimum round-trip time it has ever seen for a packet, which is basic propagation delay, because you cannot go faster than the speed of light, and if you're talking to somebody across the continent, well, but you're going to see that minimum at some point over a long time scale, and that gives you an idea of what's sort of great. We can compute then at any point in time this ratio, which we call the slowdown, which is the ratio between the exponential moving average of the VCT and what I've observed to be the minimum. And I'm going to say congestion happens. Well, this is the point of congestion. I want to avoid being here. Well, that will correspond to some VCT. We'll call that VCT star. And I'm going to say that if R is bigger than this threshold, which we'll figure out, H is going to be related to basically these quantities, then congestion is true. Yes?
So the first VM to start will have a much smaller VCT minimum than the last VM to start, but the average will eventually be the same.
Yes. And also because this is a sliding, not just that, because this is a sliding window. So this W is sliding. So even though you start at some point you got ahead of, but very soon the sliding window, it's just everybody is in it. So everybody's going to see the same min. Yeah, that's right. So it's not minimum over infinity, because then yes, you're right. Then we get these screwed up.
Is it really necessary to compute that? Isn't that where your time slice is 100% of the CPU and your VCT?
But how do I know that? So how do I know that? And how do I know, and I'm running on a host, maybe I'm running on a distributed cluster. I mean, the thing is, I really want to abstract out what I'm running on. All I do is I make progress. And I make progress, I measure, I'm assuming one thing, and I can figure out the current time. Okay, so every time I make a little bit of progress, I measure that time. And I say, well, last week, the same progress took me that much. This week, it took me that much. Okay, and the question is, if I just keep these two little statistics. Remember, I could have designed an API, talk to the host, get everything you want, but I didn't want to do that. As a matter of fact, my collaborator on this, Rich West, is an operating system guy, and he's done exactly the opposite. His thesis, his whole research is on all these APIs, QoS, reservations, and you had to see this work. We spent 2 years doing it because of all the fights we had. It's like, no, I don't want to use anything from the infrastructure. Okay, so maybe I'm taking it too religiously. And he says that. But I also I have to push back, right?
But it's good religion.
Yeah, it's good religion. It's the end-to-end religion. Okay, so remember the second question? The second question was, how do you control consumption? Well, one thing we can do is we can limit the maximum number of threads that a VM can have. Okay? So a VM could create as many threads as it wants up to a limit. You hit that limit, you cannot create more threads. Okay.
That the software running in the virtual machine sets on itself, or is that?
The VM sets for the application. So the VM will refuse to create a new thread for the application if it requests one. So you say create threads, I fail. Okay. Okay. It just sets a limit on, and the idea that these threads, are consumers of resource, and by limiting them, I can control the utilization. Well, and I'll tell you, there will be difficulty in using this for some applications, etc. So the other alternative is you can also turn yourself off. As a VM, you can say I'm going to sleep. Okay, take myself off for a little bit. Okay, periodically. So you are given the CPU, and then the first thing say, okay, sleep. So you take yourself out of the CPU or out of contention for the network. So now the thing is, the application didn't decide to do that, but the VM decided to do that, so the application are going to make progress. They're not consuming resources either. So we have these two approaches to control or limit the use of the host resources. The first one is limiting the maximum number of threads that are allowed within a VM. And the second one is simply limiting the rate with which the VM is awake. It's basically periodically sleep. Those of you who know networking will see that these are exactly the window mechanism for TCP, which says how many packets you can have en route inside the network that are not acknowledged. If you think about each packet as a consumer of resources like a thread, and by limiting that maximum number, well, you cannot send more than the window, well, that's going to be your rate, right? And some of us also know that in networking, when the number of packets you can send keeps going down because there's congestion gets to 1, I cannot go to 0. So what do? Well, instead of sending 1 every round trip time, I send every 2 round trip times. It's equivalent to sending half. That actually, I do that by sleeping. It's called timeout. That's the timeout mechanism we use here. Now, I don't want you to get the impression that you only do this when you have 1 thread. No, you can also do this if you have 15 threads. As a matter of fact, nothing stops you, at least in designing networks, from saying I'm going to have a window of 8, but I sleep half the time.
TCP packets are of the same size, so even though the analogy is great, it's based on it.
Well, all analogies have to, the time scales are very different. The resources in the network are the same. It's a buffer. Here the resources are very different. So the analogy is good, and this is where, okay, so I do have to give up a little bit to HOS at some point, but I'm still holding my, but that's the analogy. So the consumption control, just to demonstrate these two things, so here's 2 VMs, and they happen to have only 2 threads at this point, but life is good, they're making progress, there's no congestion, so they decide to add more threads. Let's say there are web servers that create threads for new requests, etc. Now, over time, they bump into each other as we're getting into congestion. They shrink again. Now, one thing you notice is that when they shrunk, they end up with different numbers. That's fine. And the whole point is, over time, everybody's doing this. So think about every VM trying to add threads, but when it realizes, oh, I pushed too much, sort of reduces the number of threads it uses. Over time, they will all converge to a fair allocation, where everybody will having basically the same number of threads. In particular, imagine a new VM now starting, and it just asks for 1 thread. Well, this 1 thread will cause these guys to squeeze a little bit. So some of them will react to this, give more room to the others, and over time, they will converge to the right allocation.
Are you assuming work conservation here? Because if you back off,
I don't kill the threads.
And you drop the number of threads down, the response time that the clients to this particular virtual machine get might be so high that they time out and waste work.
Oh, okay, I see.
So when you back off, you might be starting the trashing.
Yeah. So this is a very good point. This is a very good point. So the assumption here is if applications cannot afford this being nice, you're saying, I have a real-time application. You cannot just afford to do this for me. Well, then this is the wrong model. This is just like saying, I want to run video on the network and it's best effort. I need reservation-based. We are working on VMs that, and I'll talk about this a little bit, not much, that are a little harder to push. So basically, and they may have limits.
Even if it's not real time, there is a certain percentage of clients that give up and waste work.
Oh, that's true.
And that percentage just keeps climbing, and then it does a superlinear knee. At some point, when response time crosses the threshold.
We are not accounting for this. So this is a very good point, but we're not accounting for it. So the assumption, to answer your question, is yes, this is work preserving. Basically, you read on to, at least the assumption, we did a lot of analysis. I'll give you the point of the paper. There's a lot of analysis on, if you assume that things get lost, then it's not clear that this is the right way of doing it. So the other technique, which is the timeout, is, well, imagine that this guy has 1 thread, whether because it is really a single-threaded or because it just couldn't get any more. And now they start growing. Now, how is this guy growing in terms of its resource use without adding threads? I mean, memory, for example. It's 1 thread, but it's just eating up a lot of memory. So what happens now, you get the congestion signal, which is these arrows, and then they decide to do something about this guy can shrink. Well, this guy cannot shrink. So what it does, it stops itself, takes itself out of competition for a while and comes back.
What happens to the memory?
What happens in the memory? Well, I mean, you can argue I get swapped to disk, for example, the whole process, because you're timed out, right?
If I'm running out of a non-renewable resource, then I'm taking myself out of account. For example, if I'm running out of the commit charge on the host,
That's true.
that won't happen.
Yes. Well, but think of caching, so you're right. I mean, this
For
is.
renewable resources,
Okay, so third question is, and the answer to the third question is, so how do we adapt? Well, okay, given my network hat, I said, well, additive increase, multiplicative increase. That's what TCP does. If there is no congestion, then if you're using thread control, then you set your maximum thread number to be the maximum thread number plus some constant, which means life is good, man, add a little bit more. And if things are not good, we'll divide by some constant, let's call it B. So you exponentially slow down, but you additively probe for more resources if available. So people are, will try to go faster if they can, but not very aggressively. And in terms of execution rate, so if you decide to use timeout as your mechanism, then if there is no congestion, then your rate of execution goes up slowly. But if there is congestion, then your rate gets halved or divided by some constant. Now, the point I want to make, and I want, if you're interested now, this is a transactional networking paper with a couple of students and Ibrahim Mat, other collaborator on this work, which is there are lots of these increase-decrease rules in the literature that are very different. Like, for example, you can have quadratic increase, a multiplicative decrease. Why? Because linear increase happens to be very slow if you have a lot of resource. You're just going one at a time. Think about high bandwidth networks. Think about adding 1 to the window. Well, the window size has to go to like 800. I keep adding 1. That's not going to get me that far. So what I do is I add 1, and then I actually quadratically, increase. And it turns out that you can come up with a whole host of rules. It's a whole family. It's also infinite number of them. But the trick is they are all friendly. This is very important. In other words, you do not have to use the same increase-decrease rule to be friendly with me. So I use additive increase multiplicative. You can use something else and be still friendly. It's basically, if we live long enough, are we going to converge? That's the question. But how we converge, I can have a very drastic braking behavior or acceleration behavior, and you may have something a little slower or smoother. And it turns out these set of papers, and it started with Hari Balakrishnan at MIT, and then our work sort of closed the book on it. It's about what is the space of these additive increase multiplicative.
Is your paper penalty for the different threads not be friendly enough, or the different VMs not to be friendly enough?
So that's the key. It's not friendly enough. You're either friendly or not. It's a binary thing.
Well, I guess based on your adaptation strategy,
okay, so in this paper they talk about things like smoothness. Okay, how fast you claim available resources, that could be different. So you may be a smooth adaptation. It means it will take you longer to converge, but when things become available, it will also take you longer to grab them. So you're a smooth adaptation. And the interesting thing is, can you coexist with me while I'm not smooth, right? And the answer is yes. In other words, if we both live together, after a long enough time, you're going to get half, I'll get half. Even though we asked for things in a very different way. We can actually get to converge to the fair allocation. This is a fairness question.
Proportional fairness.
Proportional fairness. Proportional fairness. This is a very nice word.
So the friendliness definition, is that from that paper?
The TCP friendliness is actually from the networking community. Sort of, they define an equation. Say, it's, if you satisfy this equation, I don't care how you satisfy it. I don't care how you came to get to that rate. Okay, as long as over a long enough time scale you satisfy this rate, and it's related to the round trip time, the loss rate for packets, and that's about it.
So are you generalizing this work?
Yes. In this work, we show that, so people for a long time thought that AIMD was the way to get it. That basically you just have to use TCP with this particular settings in every box. And there was a paper by Hari Balakrishnan. He introduced something called binomial adaptation, where it is smoother than AIMD, but he showed that it is TCP compatible. That's the word. In other words, if you put it with the TCP that does AIMD, they are compatible. It's not like this one is going to win and this one is going to lose. They're compatible. They can live together. And what we did, he sort of think about it as he figured out a point in a space. And what we figured out is we characterize the whole space. It says this is not just this one approach. There's a whole, you can tweak lots of knobs to get this. Yes?
Can you give us any intuition as to why you get proportional? Because if you imagine a very fast oscillation between congestion and no congestion, the faster to acquire resources appears like they might on average get more of a share.
Well, so I'm not giving you total flexibility in setting these things. So if you go to this paper, you'll see that if you decide to be aggressive in acquiring things, then you have to pay the price in giving them up. Okay? And so the point is, so the guy who's smooth is actually paying for the insurance that I'm going to take things away from him fast. And the guy wants to grab, so if you're doing bulk transfer, you may want to do that. It's okay. I'll grab it fast and I'll release it fast because it doesn't matter to me. But if you're doing real time, streaming or whatever, what did I do? You say, well, okay, I can adapt, I can use a different encoding, whatever I can, but you just can't change on me every second, okay? And the trick is, well, over a minute, do they converge? That's the trick. So basically, it's over what time scale do you do the adaptation, and is the adaptation consistent with the other adaptation? Can they live together? Can they coexist? Okay, so in this particular paper, we talk about all this.
So there's also criteria in there that says if you increase,
if you increase quadratically, then you can decrease. Then your decrease rule has to be this. Mm-hmm. Okay, so basically you have 2 degrees of freedom, and if they satisfy some equations, then you are okay, and that's what this paper does. So now I talked about basically 3 dimensions of the VM. I told you how to measure congestion. I told you how to control your rates, etc. And I told you how to adapt. So how about the host? What do I want from the host? As I said, nothing, actually. As a matter of fact, if you do anything smart, you kill what I'm trying to do. Don't do anything smart. If the host tries to do anything smart, it will destroy what I'm doing. So don't. So round-robin scheduler, just best effort. It would be nice to have policing functionality. By the way, the host can figure out who's not friendly, just like the network can figure it out, because it's defined what is friendliness. Over a long time scale, I know you should get X. So this will just be an incentive for the applications to do it. The other way, which I'll talk about later, and I mentioned it, is the compiler can actually certify that things are friendly, and then you shouldn't accept anything that's not friendly. Okay? So now, of course, nobody will believe us. There's a lot of analysis in the paper, which I will show in a little bit, just some of it. But we wanted to build this. The picture you want to see is the following. Within each VM, there is a controller. There's a monitor which figures out if there's congestion or not. Informs the controller. The controller sets the rates of execution, multi-programming level, etc. Things run, results in a virtual, CT. And you have basically this repeated for every VM. Okay? That's basically the control loops that coexist on this. It turns out you can actually model this. You can write equations for it. They're all differential equations, nonlinear, etc. But you can write them. I'm going to spare you that, but the paper is there and you can really go through it. And this is an example of, for example, what happens with one setting, just to show you why this is interesting. So we start with 4 VMs, and I just started them at some random number of threads. And just let time go by. This is a numerical solution of an analytical model. You will see that they will converge to basically the same number of threads, for example. Okay? You can have weighted fairness too. So in other words, you can say, I want you to tick twice as he. Well, that's okay. That can be done as well. Okay. And by the way, by tweaking the different parameters, the shape of this adaptation can change. As a matter of fact, it could be unstable if you're not careful. It can just keep oscillating. So the nice thing about the modeling and the analysis is that allows us to at least conceptually relate. How do things converge? What are the transient characteristics? And of different adaptation techniques, different constants of the adaptation techniques, various delays in the system, what W should I use for my windows, etc. So that's but nobody will believe me. If you want to send this to Usenext conference, which we did and was accepted, they would not have accepted it with this kind of thing. They wanted to see it built. So we had to go build it. But before I show you this, I want to show you why things converge. And this is a result due to Frank Kelly, 1999, University of Cambridge, famous result. This is about why does TCP converge? Why do these things running sort of all over the place, why do they converge? So the analogy I like to use, this is not due to Kelly, even though the results are his. I'm good with analogies. He's good with math. So he uses his result, but I'll tell you what the results are. So think about the 2 elements in this equation. There is a host or a plant that sets prices, he uses that term, prices, for use of that resource. So think about the people selling you gasoline. They set the price of gasoline based on demand. More demand, the price will go up. You get close to the limit, well, it's going to be $3, $4, whatever it is. Okay? So that's the host that sets the prices. Okay, well, we're not talking about gasoline. How about virtual clock time? We just saw this curve. As demand goes up, virtual clock time is the price you pay for the service. Now, who else is playing here? Who's the other piece? The other piece are the consumers, the people who drive their cars. Based on the price of gas, you decide how much you want to drive. If price is high, you drive less. If price is low, you drive more. Well, at least we should do that. Americans don't, but we should. Which says that, okay, we have this interaction between these two utility functions. They're trying to optimize something. And by the way, every driver has one of these, because yours may be different than others. But they're all sort of in this distributed control system. And then what he shows is through something called the ANOVA analysis, that if these two functions satisfy some convexity constraints, they will converge to an optimal, this is the convergence thing. And it's optimal. The system will stabilize at that point. This is why in the previous slide, they oscillated and then they found this optimal. Okay? So,
but it's not necessarily optimal.
It is optimal. So he defines optimality. He got the Infocom award this year for this result. It's one of the...
Stability is different, right?
It is stable and it is optimal. Optimal in the sense that if you give anybody less, there will be unutilized resources. So if you give if the prices are set to anything different, then there is room for improvement for somebody. So you're not going to be happy. Let's put it this way. Well, okay, so optimization here is in terms of, are you happy? Will you change your price as a gas? So that's... so now we go to the implementation. We have to implement this. We implemented what we call the friendly UML. UML is user mode Linux. I was just, bashing it earlier, but we are using it. User mode Linux is a VM abstraction, allows people to do things on Linux. Well, believe it or not, all I talked about today is 500 lines of code implemented in one routine in UML. So you get UML, and you say, okay, Mr. UML, there is a particular routine which does the time handling. And we insert the congestion monitoring in it. And in there, we can control these global variables for number of threads and timeouts and what have you. And the code is available. We did this. So let's see. These are the control things. This you can, the configuration file, say, okay, start a UML with the following parameter. The control period is the period of time where this UML is going to sort of wake up and decide to change things. Okay, should I add more threads, remove threads, etc. It's called the control period. You can have anything you want. The window of time over which I'm going to compute that minimum VCT is 60 seconds. And all of this you can change, of course. The constant for computing the exponentially weighted moving average is 0.3. Initial limit of number of threads is 10. I mean, you have to start with something. We start with 10, so it can go up, it can go down. The slowdown threshold is 2.5. So in other words, if you want to slow down, that's the VCT average divided by VCT min. If it's more than 2.5, then you are in congestion. You can make it 3, you can make it 2, you can make it anything you want. It's just a threshold. We came up with this number based on experimentation, so you can figure this out. The IMD additive constant is 1, so you add 1 thread at a time, and the multiplicative decrease is 1.5. And the additive increase per case of rate is 0.1 hertz. So anyway, so these are, I just wanted to tell you what kind of knobs you can play with, and here are some of the evaluations. So we did a web server experiment. We do 4 VMs, each one of them running Apache 2.0, and the clients are requesting service from this Apache server, and what they're really running is a CGI script that just eats up memory. So it's a memory-bound application, not CPU-bound. Okay? And we tested the original UML and the friendly UML. And we measured the following. We wanted to look at how VCT changes. We wanted to see the throughput of the different Apache servers. And we wanted to see the fairness index, which I'll define in a second, which is how fair it is. And let me show you some example. Here's what happens to VCT if you don't have our friendliness. It just as the number of, so this is the load from the client. So you have these generators who generate requests. And as the requests increase, if you don't do anything about it, best effort, keep creating new threads, well, VCT is going to shoot up. Not surprising. Of course, if you do adaptation, why would you shoot up? You're actually not. You're just deferring the clients. They're going back to Abdus Salam. Well, maybe the clients will time out. Okay, well. But at least I'm not inefficiently using the infrastructure. And here's an example of what happens in terms of throughput, number of requests per second. Again, you see the drop for the regular UML, and we keep ourselves up here. Okay? Now,
at the right side of these slides, the machine starts crashing.
At the right of these slides, we could not generate more than this, actually. I mean, it goes down slowly. It doesn't, I mean, why would it? You're just denying, you're not answering clients' requests. What happens on
I mean, the red now.
Oh, yeah, the red one, of course, the red one will crash, yeah. The red one, that's it. But I was told you asking about the blue line, which is where we would go. I mean, okay, so we go down slowly, but the key point here is what happens is the clients. So one thing to realize is, just going back to, again, Abdus Salam's point, it is not that we're serving all the clients. We are just doing admission control, basically, right? Because the clients are not going to, you know, they wait for it. I mean, this is the HTTP request generator will just wait for its request to be generated. Yeah. So in many ways, it's throttling the clients.
Yeah, so you keep your machine from the blue line, you keep from crashing.
Absolutely. Absolutely. And that's the point of this. The point of this is, but I'm doing this by doing no host OS resource allocation, nothing. Okay? And this is memory, this is not CPU. So you can also do it first. We tried the CPU one, the curves were not as beautiful, but you can see the same trends. Well, this is what happens for different HTTP servers. Now, here's something interesting about Linux. When Linux thinks it's in, so up to this point there is no thrashing, so things are happy. When Linux gets into thrashing, it does the following. It says, oh, okay, well, you know, put you on the shelf. Put one of them on the shelf. You get zero. The throughput is zero. One of them gets rich because, you know, Linux way to act with thrashing is to actually make one very rich and everybody else just out. It's the equivalent of just, you know, swapping them to disk. Which you can see that this is a problem. Now look at what happens with us. Now, remember, I'm not saying that there is no burstiness here. You know, one did end up going zero for a while, but over time they do converge. So this is what they get in terms of throughput. Okay, this is normalized throughput in case you wonder what the answer is. And here's fairness. Now, fairness is defined, it's this complicated thing. It's basically saying how far away I'm from the optimal. Assume I had a perfectly optimal system, which divides everybody exactly by 1 over n. So you really want this to be 1. Now, you can see with low load, everything will be fair because nobody's suffering. Everybody will be the same. As the load increases, UML drops. We don't. We do a little bit, but not, you know, this is actually quite a result. Yes?
Something a little surprising, because the context switching overhead in the host should grow. Well, it is actually shown, because you have a linear drop in throughput, in the total throughput,
yeah.
And that's the context switching overhead.
But there's no context switching, the context switching between the VMs. Well, I guess within the VM there's also overhead of context switching within the...
Has context switching overhead on the physical process.
That's right, and then there's context switching.
Growing as you allow a higher degree of multi-programming.
No, but the multi-programming is within the VM. The degree of multi-programming is within the VM. So you are the application, you are the VM. The fact that you're getting more threads inside of you, the context switch is paid when I go from one VM to the other, not when I go from one thread within the VM to another thread within the same VM. I don't know if this makes sense. But
the overhead of the OS is actually superlinear in the number of VMs that you can run.
Yes, that is true. That is true.
The running axis.
Yes, you are right. But remember that what I'm adding here, I'm not changing the number of VMs. I'm changing the load on each VM. This is not 80 VMs. This is the number of, this is the load on, I only have 4 VMs. So the number of VMs didn't change. We have other experiments where the number of VMs changes. I may have them actually. No, I don't have them. But again? Oh, this one, yes.
Oh, it says number of VMs.
Oh, yes. Okay, so this is what you're talking about. So, yes, and that's actually, okay, that's exactly your point. I'm sorry. That's what happens when you're an advisor. You forgot what your student put on the slide. No, you're absolutely right. So here the load was number of sessions per VM. Here we fixed the number of sessions per VM. We just added VMs just to show different ways of looking at load, basically. And here you can see that, yes, it will stay up, but here you pay a price for the context switching. All right. Okay, well, just to go back to this point, now I'm going to talk about sort of the interesting research out of this. Food for thought. The first thing is friendly wrappers. So we did this, we took a VM, we added our 500 lines of code. Well, let's say we're in a world where people write applications and the application can share the host. Can we ensure that an application is friendly even though it was written by an average, C++, Visual Basic, whatever programmer? Yes, if the compiler knows how to do this. So the idea is, could an application be made friendly post-mortem? It was written, it's there. Can I make it friendly? Yeah, just wrap it up in a friendly sort of envelope and say, okay, now I'm friendly. In many ways, this is, and now I'm showing the colors of the research I'm doing with programming languages folks, where they're saying friendliness really is an attribute of an application. It's a type. And this application is typed as friendly. It's stamped as friendly. And we're actually looking at how compilers can do this. Compiler could ensure that I add the right code to do this friendliness for an application. So here we show, for example, two different applications. So these are two different applications, not a web server and a web server running on a VM and the same VM. No, these are two different applications. And so clearly they have very different concepts of the resources they use and so on. And you can see that throughput-wise, granted they are going to get different throughput because they are actually doing different things. But you look at the turnaround time for the thread, how frequently do they get service, and you can see that they sort of oscillate about the same value. And this was done by having a wrapper around them. So we took the application, just added a wrapper around it to do that. If we haven't done that, you'd ask me, so what would be the performance if you didn't do that? These lines would have just stayed where they are when they started. This red line, it would have just stayed like this. They wouldn't have converged a little bit. Okay? More food for thought. Well, I assume, and this, of course, many of you asked that question, how could you just stop threads or control threads? What if all threads are not created equal? Which thread should I suspend? Well, okay, actually in this experiment, the max is what we change. But you can also imagine a situation where you really literally suspend threads because you really want to reduce the number of threads. Which ones would you suspend? Which knobs do I expose to the programmer? So far, I've assumed I want the programmer to do anything, but maybe there is a room for a programmer to tell me, okay, this thread, don't touch this thread for adaptation. You cannot sort of mess with this. Or this is okay, this is best effort. You can reduce the number of threads of this pool, but not of that pool. Okay? So questions here is about, could this be typed? Could I get some information from the programmer? Finally, and this is very interesting, and what we have done so far is a passive feedback signal. I'm just sitting there measuring this VCT passively. Well, I'm interested in this one. Could the compiler insert a benchmark in the application, in the VM itself, to probe the congestion of the system? So now, instead of just measuring VCT, I have a little piece of code, and every time I feel like it, I can run it and see how long it took on the VM. Well, if it took 1 second now, 10 minutes later it takes 2 seconds, well, I'm twice as loaded as a minute ago. So in many ways, you can think that there could be inline benchmarks inside your application that are inserted by the compiler for the sole purpose of getting these congestion signals. And you may have some of them different benchmarks for different resources. Maybe I have one for the network, one for the CPU, etc.
So what these benchmarks would give you would presumably be faster convergence to...
No, it will give you better. So far, this is like saying in the network, when you lose the packet, you don't know where it's lost. And you don't know if it's a wireless loss or a congestion loss or error correction loss. I mean, you don't know why you lost the packet. So think about this as a mechanism to allow the endpoint better idea of the state of the congestion. Not just say faster congestion. I mean, yeah, you get faster signals, so yeah, you can probably react faster, but also more specific. Like I want to find out, so right now VCT is everything. It's the feedback, it's the time it took me between this point and that point, which accounts for CPU, memory, network, anything that I used during that period of time. But maybe you want just to measure one resource. then you may want to put a benchmark that will test that resource inside your code, generate the congestion signal just for that. In this case, you may have multiple feedback signals, not just one. Okay? I did talk about AIMD, but as I mentioned, it will be interesting to study like PI controllers, PID controllers, SIMD controls, and a bunch of others. And finally, going back to my original problem, which was that Sensorium, we only tried this on one box. What would it look like if a whole cluster and you're running basically these entities on a cluster? How would it look like? Take-home message is VM friendliness. It is the incarnation of the end-to-end argument for multi-resource management in a shared hosting environment. Remember, I didn't react to a particular resource. I just reacted to this congestion signal. VM friendliness is really an etiquette. It's an etiquette for writing applications. It's an etiquette that compilers can enforce to just make sure that a hosting environment is shared fairly. And okay, we implemented it, etc. So this is the paper. It was just published less than a month ago in the ACM Usenix Virtual Execution Environment Conference, which I strongly encourage anybody interested in this to really attend and contribute to. It was a wonderful meeting. Very, very, and people from, there were a couple of people from Microsoft. I didn't see too many, but certainly the quality was very high, so I recommend it. Thank you. And I'm very sorry about being late, but questions or... Great, thank you.
Good work.
Well, actually, I have more slides, but this is more of this because I feel like this is a very sort of nice part of the Sensorium stuff. So what I've seen in you is I'll show you what the snafu language will look like. We love acronyms in our department. This is what it would look like. Use a camera, take a snapshot, find the face in it, and then identify the face. Okay. Now I can also say, and by the way, this stream should be private, and only make it public. For example, you will do face count. You can tell people how many faces are in this room, but don't show them any face. So more like a functional style, you can sort of constrain things. And you can write programs like this. My wife can like this. You say, okay, here's a trigger. If you detect motion in this camera and it's between 2 a.m. and 4 a.m. in the morning, then take a snapshot and send it to security. Tell them my husband should not be in his office in 24. This is the step representation. So basically, if you look at this program, it's nothing more than this tree, where these are the ingredients. This is what I actually mapped to the Sensoria, and then picture is I can send this piece of the tree to this machine, this piece to this machine, take a snapshot, etc. on the sample itself, and then that goes on. These are the execution routes I talked about. And one thing we want to develop is visual execution environments to host multiple of these guys on the same. This is just fun. I can show that you have different programs. People write different programs. But you can find common pieces in it. Because you're using the same camera, getting the same feedback.
That's cool. That's interesting. That's very neat.